Hello everyone. In this video, let's learn how we can design a circuit for a full adder using NOR gates only. For NOR gates, we can start by the product of some Boolean expression for the sum and for the cout, and we can use K-map to get the minimal form. So let's see how we can do this. For the POS form, unlike the sum of product, the SOP. In SOP, we group ones together. In POS, we need to group zeros together. So for the sum, we don't have any adjacent zeros, so they have to remain separate. So we have 1 0 in this area. We have another one in this area. We have another one in this area. Let's use another color. And we have another one in this area. So let's see how we can write the product of sum. So S will be equal to, from the one in green, A is 0, so we need to treat it as A plus B and Cn are zeros, so this is plus B plus Cn. For this 0 here, I circled in pink, so we have A is 0, so this will be A plus B is 1 and Cn is 1, so this will be B bar plus Cn bar. And then from the term in blue, A is 1, so this will be A bar plus B is 0 and Cn is 1, so will be plus B plus Cn bar. And then for the last 0, A is 1, so this will be A bar plus B bar because B is 1 and plus Cn. So this is the Boolean expression in POS form for the sum. So let's do the same thing for the cout. So cout will be equal to. So let's see how we can group zeros in this one. So this 0 here can be grouped with this one. And then this 0 here can be grouped with this adjacent one next to it. And then for this 0 here, we can group it with this one. For the group in green, A is changing from 0 to 1, so we don't have to worry about it. B is 0 and Cn is 0. So this will be B plus Cn. The group in red, A is 0 in this row, so this will be A plus. From here to here, B is not changing and it's 0. So this will be plus B. And then the group in blue, in this row, A is 0, so this will be A plus. From here to here, Cn is not changing and it's 0. So this will be plus Cn. Now we can take these two Boolean expressions and design our circuit. So let's start with the cout first. So for the cout, we have multiplication, so that means we need an AND gate first. And then this output will be the cout. And then we have 3 terms multiplied together. So that means we need 3 inputs. So this is the first input, this is the second input, and this is the third input. From the first group, we have B plus Cn. So for plus, we need an OR gate. So this is an OR gate. And then it takes 2 inputs, B and Cn. The second term in red is A plus B. Also, we need another OR gate. And this is A plus B. The third term in blue, we have A plus Cn. So that's an OR gate, and the inputs are A and Cn. Now, how can we convert this to a NOR gates only? So we can do this similarly as we did in the previous video for NAND gates. We can add a NOT gate twice on each signal wire here. So we add twice, we added twice on this signal wire, and then we added twice here, 2 NOT gates. Now an OR gate followed by a NOT gate, this is a NOR gate, and an AND gate with NOT gate on every single wire of its inputs, this is equivalent to a NOR gate. So now we can rewrite this circuit for the Cout in form of NOR gates only. So this is the NOR gate, Cout, and then here we have 3 NOR gates. And we have 3 inputs, A, B, and Cn. And now we can know how to wire them. So at the top NOR gate we have B and Cn. So we can get B and Cn. For this one we have A and B. So this is A. And this is B. And then for the bottom one we have A and Cn. So this is A, we can take it from here. And this is Cn. Next we can do the same thing for the sum. So we have 4 terms multiplied by each others. So that means first on the output we need an AND gate with 4 inputs. So this is the sum. So for A plus B plus Cn we have an OR gate. And then we have another one for A plus B bar plus Cn bar. We need another one for the one in blue, A bar plus B plus Cn, and we have another one for A bar plus B bar plus Cn. They're all fed in this AND gate. So for the first one in green, we have A plus B plus Cn. That's A, B, Cn. The one underneath it, we have 3 inputs as well. So let's draw all the inputs, and they all have 3 inputs. So this, the second one is A, B bar, Cn bar. The one in blue, third term, we have A bar, B, Cn bar. And then the last one in red, it's A bar, B bar, Cn. So next, to convert this to a NOR gates, we can add NOT gate twice on the signal wire because this doesn't change the signal. And another one here. And similarly, this one here will be a NOR gate, and each one of these, an OR gate followed by a NOT gate, is a NOR gate. So now let's redraw our circuit. So here we have a NOR gate, the output is the sum, and then we have 4 NOR gates. And then as we see, sometimes we need B bar, Cn bar, and A bar. So to do this using NOR gate only, we can use 2 inputs, NOR gate, and then feed A to both of its inputs. So this is A, on this side we get A bar. Similarly, we can do that for B input using a NOR gate, and then feed B to both of its inputs. On this side we get B bar. And also similarly for Cn, we use a NOR gate with 2 inputs and we feed Cn to both of its inputs. So on this side we get Cn bar. Now the rest is just like connecting to these NOR gates. So the first one we need A, B, and Cn. So we can get A from here, B from here, and Cn from here. For the one underneath it, the second one, we need A, B bar, and Cn bar. So we can get A from here, B bar we can take it from here, and Cn bar we can take it from here. And then similarly for these two, we need where to get them from. So we need 3 inputs for this one, which are A bar, B, and Cn bar. And also we need 3 inputs for this one, which are A bar, B bar, and Cn. So now this is how we can design the circuit for a full adder using NOR gates only. So inside the full adder circuit, we will have this circuit here for the sum, and then we have this circuit here for the cout. I hope this was helpful. Thanks for watching.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.